Now we come to chapter 4, module 2. Here I shall state two important theorems associated with symmetric kernels. One is Hilbert-Smith theorem and the other is Marcer's theorem. Then we consider some examples where we will apply Hilbert-Smith theorem to solve Fredholm integral equation of second kind with symmetric kernel. We consider Fredholm integral equation given by equation 4.16 where kxt is the symmetric kernel. We will solve this Fredholm integral equation by using Hilbert-Smith theorem. So, we first state Hilbert-Smith theorem. Let lambda 1, lambda 2, lambda n etc. be eigenvalues of a symmetric kernel kxt where x and t both lie in the closed interval AB and phi 1 x, phi 2 x etc. phi n x are the corresponding orthonormalized eigenfunctions. Then if kxt is absolutely square integrable in the square AB cross AB and if a known function hx is also absolutely square integrable in the closed interval AB, then we can express the function fx given by integral a to b kxt ht dt in series as given by equation 4.17. In the series given by equation 4.17, the coefficients fn are given by equation 4.18 and it is the inner product of the functions fx and phi nx. We may note here that we have not assumed that the set of eigenfunctions is complete. Now the coefficients given by equation 4.18, which is the inner product of the functions phi, n and f, can be written as fn equal to 1 by lambda n into inner product of hx and phi nx, and so that the series 4.17 fn can be replaced by 1 by lambda n into the inner product of h phi n. So, we get fx equal to summation n equal to 1 to infinity hn by lambda n into phi nx, where hn is the inner product of hx and phi nx as given by equation 4.21. Now, we can show this in the following way. Phi nx are the orthonormalized eigenfunctions, so it satisfies the homogeneous integral equation given by phi nx equal to lambda n integral a to b kxt phi nt dt x lying in the interval a to b. Kxt is the symmetric kernel. Now, we take the complex conjugate and it can be noted that the eigenvalues lambda n are real and kxt is symmetric. So, we obtain after taking complex conjugate that phi n bar x equal to lambda n integral a to b k tx phi n t bar dt x lying in the interval a to b. Now we multiply this equation on both sides by the function hx and integrate with respect to x from a to b to obtain integral a to b hx phi n bar x dx equal to lambda n integral a to b hx dx integral a to b k tx phi n bar t dt. Now the left hand side, as you can see, is the inner product of h and phi n x, so that it can be written as hn, and in the right hand side we interchange the order of integration to obtain hn equal to lambda n. Outer integral is a to b phi n bar t dt and the inner integral is a to b k tx hx dx. Now we know that the function fx is equal to integral a to b kxt ht dt, so that the inner integral can be written as ft. So the expression becomes hn equal to lambda n integral a to b ft phi n bar t dt, where n ranges from 1 to etc. So the integral a to b ft phi n bar t dt, this is the inner product of the functions ft and phi n t, and that is given by fn by equation 4.18. So that we get hn equal to lambda n into fn. So fn can be written in terms of hn, and hence the series for fx can be written as fx equal to summation n equal to 1 to infinity hn by lambda n into phi nx dx, as we wanted to show it. Now we come to the Fredholm integral equation, and we shall apply Hilbert-Smith theorem to solve Fredholm integral equation of second kind as given by equation 4.22, where the kernel kxt is symmetric kernel. Now we express the equation 4.22 as phi x minus lambda gx equal to fx, where gx is the integral from a to b kxt phi t dt. Now using Hilbert-Smith theorem, we can write this function gx in the series form as gx equal to summation n equal to 1 to infinity a n phi nx by lambda n, where a n is the inner product of the functions phi x and phi nx, and phi nx are the eigenfunctions corresponding to eigenvalues lambda n. So using 4.23 and 4.24, we can write phi x as fx plus lambda summation n equal to 1 to infinity a n phi nx by lambda n, as given by equation 4.25. Now we multiply equation 4.25 by phi m x bar and integrate with respect to x from a to b to obtain integral a to b phi m bar x phi x dx equal to integral a to b phi m bar x fx dx plus lambda into summation n equal to 1 to infinity a n by lambda n into integral a to b phi m bar x into phi nx dx, where m ranges from 1, 2, 3, 4, etc. Now, we know that am is the inner product of phi and phi m, so that the left hand side of this equation, that is this expression, becomes am, and also we know that fm is the inner product of the functions fx and phi m, so that first term on the right hand side is fm, and phi n and phi m, its inner product is given by the integral a to b phi m bar x into phi nx. So the second term of the right hand side, that is this term, is the inner product of phi n and phi m. So this whole equation becomes am equal to fm plus lambda summation n equal to 1 to infinity an lambda n into inner product of phi n and phi m, as given by equation 4.26. Now we know that phi n are the orthonormalized eigenfunctions corresponding to eigenvalue lambda n. So since phi n's are orthonormalized, so the inner product of phi n and phi m, this is equal to 0 for m equal to n and equal to 1 for m equal to n. So that in the expression given by equation 4.26, we find that in the summation on the right hand side, when m is equal to n, then this inner product of phi n and phi m becomes equal to 1, and otherwise it is equal to 0. So that the summation on the right hand side reduces to only one term given by am by lambda m. Hence, we obtain from equation 4.26 am equal to fm plus lambda by lambda m into am, from where we obtain am as lambda m into fm divided by lambda m minus lambda. M is 1, 2, 3, 4, etc. So we have obtained am, and if I substitute this am in equation 4.25, we obtain the solution of the Fredholm integral equation given as phi x equal to fx plus lambda into summation n equal to 1 to infinity fn divided by lambda n minus lambda into phi nx, as given by equation 4.27. Now, there arises two cases. In case 1, if lambda is not equal to lambda n in the equation 4.17, then phi x given by equation 4.17 gives the unique solution of the given integral equation 4.22. But in the second case, that is case 2, if lambda is equal to lambda n in the equation 4.17, then the equation 4.17 will make no sense if fn is not equal to 0. In that case, the integral equation is inconsistent. But if fn is equal to 0, that means fn means the inner product of f and phi n. If that is equal to 0, then f is orthogonal to the eigenfunction phi n, and in that case the non-unique solution of integral equation 4.22 will exist. Now if lambda becomes equal to lambda n for some value of n as m, that is lambda equal to lambda m, and also fm, that is the inner product of f and phi m, is equal to 0, then from equation 4.27 we find the non-unique solution of the integral equation 4.22 as phi x equal to fx plus lambda into summation n equal to 1 to infinity n not equal to m fn into phi nx divided by lambda n minus lambda plus alpha m into phi mx as given by equation 4.28. Here alpha m is arbitrary constant. So this gives the non-unique solution of the given integral equation 4.22. Now we state another important theorem associated with symmetric kernel, and that is known as Marsh's theorem. This theorem states that let Kxt be a continuous symmetric kernel in the square AB cross AB, and let the corresponding non-negative integral operator generated by Kxt over all absolutely square integrable functions on the closed interval AB be capital K. Then if capital K phi is equal to summation n equal to 1 to infinity phi n, that is the inner product of phi n divided by lambda n phi nx as given by equation 4.29 in terms of the eigenvalues lambda n and the corresponding orthonormalized eigenfunctions phi n x, we have Kxt equal to summation n equal to 1 to infinity 1 by lambda n into phi n x into phi n bar t as given by equation 4.30, and the series converging absolutely and uniformly with respect to both variables x and t. The expansion 4.29 for capital K phi is known as the spectral expansion of the operator K. Now we shall consider some examples and we shall use Hilbert-Schmidt theorem to solve Fredholm integral equation of second kind with symmetric kernel. We consider example 1. Use Hilbert-Schmidt theorem to solve the following integral equation given by equation 4.31, where the kernel is given by Kxt equal to x into 1 minus t for x less than t and t into 1 minus x for x greater than equal to t as given by equation 4.32. Kernel Kxt and fx both are square integrable functions in the closed interval 0 to 1. Now we shall solve this integral equation. It can be noted that the kernel Kxt as given by equation 4.32 is symmetric. Now the homogeneous integral equation corresponding to equation 4.31 using the kernel as given by 4.32 can be written as phi x minus lambda integral 0 to x t into 1 minus x phi t dt minus lambda integral x to 1 x into 1 minus t phi t dt equal to 0 as given by equation 4.33. Here we have broken the integral 0 to 1 into two integrals 0 to x and x to 1. Now differentiating with respect to x, we obtain phi dash x plus lambda 0 to x integral t phi t dt minus lambda integral x to 1 minus t phi t dt equal to 0. Again differentiating, we obtain phi double dash x plus lambda phi x equal to 0, where the dash or double dash denotes the differentiation with respect to x. Now from equation 4.33, we observe that phi 0 is equal to 0 and phi at x equal to 1 is also equal to 0. So the homogeneous equation 4.33 is equivalent to an ordinary differential equation d2 phi dx2 plus lambda phi equal to 0, x lying in the interval 0 to 1 as given by 4.34, with the boundary conditions phi at x equal to 0 and phi at x equal to 1 is equal to 0 as given by equation 4.35. Solving this boundary value problem, we obtain phi x equal to a cos root lambda x plus b sin root lambda x. The boundary condition phi at x equal to 0 gives capital A equal to 0, so that phi x is equal to b sin root lambda x. Now we apply the second boundary condition, that is phi at x equal to 1 is 0, and this gives for b not equal to 0 sin root lambda is equal to 0, because we are not interested in trivial solution. So sin root lambda equal to 0 gives lambda equal to n square pi square, n ranges from 1 to etc. Hence the eigenvalues and the corresponding orthonormal eigenfunctions can be taken as lambda n equal to n square pi square and phi nx equal to root 2 sin n pi x, where n ranges from 1 to etc. as given by equation 4.36. Now if I use Hilbert-Smith theorem by using equation 4.27, we can say that the unique solution of the given integral equation is obtained as phi x equal to fx plus summation n equal to 1 to infinity 2 lambda divided by n square pi square minus lambda square into integral 0 to 1 ft sin n pi t dt into sin n pi x, or this can be equivalently written as phi x equal to fx plus integral 0 to 1 capital R x t lambda f t dt for lambda not equal to n square pi square. Here the resolvent kernel capital R x t lambda is given by the formula R x t lambda equal to twice lambda summation n equal to 1 to infinity sin n pi t into sin n pi x divided by n square pi square minus lambda for lambda not equal to n square pi square. So we get the unique solution of the given integral equation when lambda is not equal to n square pi square. If lambda is equal to m square pi square for some positive integer m, then either the given integral equation has no solution or has a unique solution, and this unique solution will exist if the inner product of ft and phi mt is equal to 0. That is, f is orthogonal to the eigenfunction. That is, this inner product equal to 0 can be written as integral 0 to 1 fx sine m pi x dx equal to 0. If this happens, then non-unique solution of the given integral equation will exist, and this non-unique solution is given by phi x equal to fx plus alpha m sine m pi x plus integral 0 to 1 L x t lambda f t dt as given by equation 4.38, where the function L x t lambda is given by summation n equal to 1 to infinity, where n not equal to m, twice lambda sine n pi x into sine n pi t divided by n square pi square minus lambda, and lambda is not equal to n square pi square as given by equation 4.39, and alpha m appearing in equation 4.38 is an arbitrary constant. Next, we consider example 2. Use Hilbert-Smith theorem to solve the following integral equation given by phi x minus lambda integral 0 to 1 minimum of x and t phi t dt equal to x, x lying in the interval 0 to 1. Here the kernel of the integral equation given by 4.40 is the minimum of x and t. Now equation 4.40 can be written in the form phi x minus lambda integral 0 to 1 k x t phi t dt equal to x, x lying in the interval 0 to 1. If I compare this equation with equation 4.40, then we find that the kernel kxt is equal to t when t is less than x and is equal to x when x is less than equal to t. We can see here that the kernel is symmetric and square integrable. Now we shall use Hilbert-Smith theorem to solve this integral equation. Now the homogeneous integral equation corresponding to integral equation 40 can be written in the form phi x minus lambda integral from 0 to x t phi t dt minus lambda x integral from 0 to 1 phi t dt equal to 0. Here we have broken the integral from 0 to 1 into two integrals, that is from 0 to x and from 0 x to 1. This on differentiation gives phi dash x minus lambda integrals x to 1 phi t dt equal to 0. Again differentiating, we obtain the following boundary value problem for phi x as phi double dash x plus lambda phi x equal to 0 as given by equation 4.41 with the boundary conditions phi 0 equal to 0 and phi dash 1 equal to 0 as given by equation 4.42. Here dash means differentiation with respect to x. Now if we solve the boundary value problem 4.41 and 4.42, we obtain phi x equal to capital A cos root lambda x plus capital B sin root lambda x. Using the boundary condition phi at x equal to 0, we obtain capital A equal to 0, so that phi x is equal to B sin root lambda x. We are not interested in trivial solution, so we use the boundary condition phi dash 1 equal to 0, which gives us cos root lambda equal to 0, and this gives lambda n equal to lambda n, that is equal to 2n minus 1 whole square pi square by 4, and n ranges from 1 to etc. So that the eigenvalues and the corresponding orthonormal eigenfunctions in this case are given by lambda n equal to 2n minus 1 whole square pi square by 4 and phi nx equal to root 2 sine 2n minus 1 pi x by 2. Thus, when lambda is not equal to lambda n, that is 2n minus 1 square pi square by 4, then we obtain the unique solution of the given integral equation as phi x equal to x plus lambda summation n equal to 1 to infinity fn divided by lambda n minus lambda into phi nx from the Hilbert-Smith theorem, where fn is equal to root 2 integral 0 to 1 x sine 2n minus 1 pi x by 2 dx, which can be evaluated as fn equal to minus 1 to the power n minus 1 4 root 2 divided by 2n minus 1 square pi square. So, this is the unique solution of the given integral equation when lambda does not coincide with any of the eigenvalues. If lambda coincides with lambda n, then the given integral equation is inconsistent, as fn can never be equal to 0. Thus, using Hilbert-Smith theorem, we have obtained the unique solution of the given integral equation. Thus, in chapter 4, we have learnt about the properties of symmetric integral equation of second kind, and also we have stated two important theorems in connection with symmetric integral equation of second kind, and used Hilbert-Smith theorem to solve Fredholm integral equation of second kind with symmetric kernel. This concludes chapter 4.